Hello. In this lecture, we will be going over multivariate statistical analysis. We will be focusing on multiple linear regression mainly. So first of all, let's talk about multivariate data analysis. Basically, when we need to conduct multivariate data analysis, that means we have 3 or more variables involved. Instead of looking at the relationship between 2 variables, we may want to know whether several factors can affect one dependent variable, or we want to find out whether certain variables are similar to each other. So depending on the purpose, we could do dependence techniques. We can also do interdependent techniques. For dependent techniques, as I just mentioned, we want to explore the relationship of several variables with one dependent variable, which is typically labeled as y. Okay, and for this purpose, we'll be using multiple linear regression. Multiple linear regression is just an expansion of the simple linear regression we'll talk about in the previous chapter. Okay, recall that in simple linear regression, we are looking at the relationship between y, the dependent variable, and x, the independent variable. Now, in multiple linear regression, what we are looking at is the relationship between several axes, okay, several axes, and one dependent variable y. We're going to have x1, x2, x3, etc. And we want to explore the relationship of these axes with y. The other technique, which we will not go over in this lecture, though, is the interdependence technique. Okay, and for this, we have a set of variables. Okay, apparently we should have more than 3 variables, and we want to kind of group things together. And for that case, we will do factor analysis, right? Okay, let's talk about multiple regression analysis. Here's the multiple regression model. If you take a look at the model, it's quite similar to the simple linear regression model with a few extra terms. So for the simple linear regression model, we have y equal to alpha plus beta times x. Now, for multiple regression analysis, since we are looking at more than one independent variables, that is more than one x, we're going to have x1, x2, x3, and this is I guess it's a weird term when PPT is converted to connect what the platform we're using for the lecture. So this should be okay. So right here, we're including more than one axis. And basically, this model is quite general, saying that we can include n axis, and n takes any integer depending on the situation. Lastly, we still have the error term up there. Now, if you think about it, for any dependent variable, there ought to be more than one factors that could affect the dependent variable. For the example we were talking about last time, the relationship between the price of old car and the mileage. If you think about it, yes, mileage is definitely one important factor that determines the price of a used car, but other than that, we could definitely say that the year of the car matters, the condition of the car matters, the number of accidents happen to the car matters. So there are more than one factors that could affect the car, could affect the price of the car, and therefore, realistic speaking, we should include all these factors. And that's why we need to explore multiple regression analysis. Now, same as before, y is our dependent variable, x are the independent variables, and alpha and beta are the parameters to be estimated using sample data. Basically, we're going to collect data on y and the several axes there. We'll run the regression analysis, and then we'll be able to get the estimates for the alpha and betas. If you can recall, when we're talking about simple linear regression, we said we could include categorical variable in regression. And that answer is the dummy variable. We could use dummy variable to include categorical variable. Now, typically, if it's a simple linear regression model, we usually do not use it if our independent variable x is categorical. Now, for multiple linear regression, okay, if we want to include categorical variable, we can do so. So how can we create this dummy variable? Okay, for the dummy variable, let's come back to these 2 points later. For the dummy variable, how do we define it? So the dummy variable is basically sort of a switch. We will switch the dummy variable on when the observation has certain characteristics. That's the idea. So the dummy variable d will equal to 1 if characteristic appears, and we'll take the dummy variable d equal to 0 if characteristic. That's the basic idea. And let me show you one example really quick. Suppose in analyzing revenue data for a retailer, we realize that the season matters. That is, if you look at the data, there's seasonality in it. And we still want to run regression analysis to analyze the revenue data, at the same time include the 4 seasons. Then we could create dummies to represent the seasons such that we could create x1, that's the first dummy, and we take x1 equal to 1 if the observation is referring to season 1. Otherwise, x1 will take a value of 0. Now, we could take x2 to represent the second season, and x2 equal to 1 if the observation is referring to season 2 and 0 otherwise. Same for x3, which represents season 3. You might, at the very beginning of learning dummy variable, you might intend to create another dummy variable for season 4. However, in regression analysis, that is not doable, okay? Because there's something called multicollinearity. That means the axes are highly correlated. Now, if you create 4 dummy variables for the 4 seasons, which is the 4 categories for your categorical variable, then you will find that the 4 dummy variables are perfectly correlated. And whenever that happens, it is impossible for you to estimate the model, okay? And so this goes back to the point back here. It says for a variable with n categories, we create n-1 dummy variables to represent the first n-1 categories. Just as we did here, since we have 4 categories for this particular variable, seasonality, okay? We have 4 seasons, so we're gonna create 3 dummy variables to represent the first 3 seasons. What if we are looking at an observation that belongs to season 4? If that's the case, then we will find that all 3 dummy variables we created will take a value of 0. And whenever these 3 are equal to 0, that means we're looking at an observation that belongs to season 4. And lastly, we do have a name for the category that we are omitted, or for the category we didn't use dummy variable for it. It's called the omitted category, and the last one is usually the one omitted. Okay, it is represented when all dummy variables take a value of 0. Right? Okay. So let's take a look at several examples and see how we can use multiple regression analysis to test about this and to answer certain questions in business. It says, assume that a toy manufacturer wishes to explain store sales, which is the dependent variable, using a sample of stores from Canada and Europe. Okay, and they are interested in several factors. Therefore, they set up several hypotheses. And they want to use the multiple regression analysis to test these hypotheses. The first one says, competition sales are related negatively to sales. And the second one says sales are higher in communities with the sales office than when no sales office is present. And the third one is grammar school enrollment in the community is related positively to sales. Okay. Now apparently, based on these hypotheses, we found out there are several factors could potentially be related to the sales. So the sales as our dependent variable will be represented by Y, and the three other factors will be represented by X. These are competitive sales, community with a sales office, and grammar school enrollment. So these three should be our independent variables. Suppose we set up the model, collected the data, and estimated data. And we found the following regression line. If you wonder how come we have this regression line, well, the process is the same. Recall that when running simple linear regression, we just use Excel's add-ons data analysis, then we just run regression. Okay, I'll show you later with CS data, but let's assume that using the data, we can estimate the alpha and betas, and eventually we got the following regression line. Okay, the Y here actually should be Y hat, although it's not quite clear. Again, this is because when the PPT file is converted, there will be some twists and distortions. So Y hat is equal to 102.18 plus 0.387x1 plus 115.2x2 plus 6.73x3. And here, x1 represents competitive sales. x2 is a dummy variable for sales office. It is equal to 1 if a sales office is present. It is equal to 0 otherwise. And x3 is grammar school enrollment. Now, let's focus on x2 for a minute. If you think carefully, this dummy variable x2 is just like a switcher, right? Whenever the community has a sales office, we'll switch this dummy variable on and assign 1 to the variable. Whenever there's a community without a sales office, we'll switch this variable off and assign 0. Okay, so that's the nature of dummy variable. And using dummy variable, we're not able to include a categorical variable in our regression analysis. Now, as we mentioned in simple linear regression analysis, the coefficient, the slope coefficient, tell us the changing Y when X changes by 1 unit. That interpretation carries to our multiple regression analysis, but we need to add something more, okay? For example, if we're looking at 0.387, okay? This 0.387 describes the relationship between X1, which is competitive sale, and Y, which is the sales of this company. It also tells us when competitive sales increase by 1 unit, the change in the company sale will increase by 0.387, okay? And then we should also mention that when we ask X1 to increase by 1 unit, at the same time, we are holding X2 and X3 constant. So that's something very important to keep in mind. Whenever you try to interpret the coefficient for multiple regression analysis, okay, you're gonna always need to mention that you're only changing one X, but keeping the others constant. Now, with these numbers, we can have a rough idea about the hypothesis, okay? I said rough ideas because we are making our judgment purely depending on the numbers, okay? So if you look at the first coefficient, 0.387, that is saying that competitive sales is positively related to the company sales. And if you go back to the first hypothesis, it says competitive sales are related negatively to sales. And therefore, by just looking at the coefficient, we are able to tell hypothesis 1 is not supported, since they are apparently should be positively related. The second coefficient, 115.2, is positive. That means x2 and y are positively related. Let's go back to the second hypothesis. It says sales are higher in communities with a sales office than when no sales office is present. Now, this basically tells us we expect a positive relationship between this categorical variable and our dependent variable sales, which is confirmed by the coefficient positive 115.2. So hypothesis 2 is supported. Lastly, hypothesis 3, we're going to look at this coefficient, 6.73. That means x3 and y are positively related. Now let's take a look at the hypothesis. It says grammar school enrollment in the community is related positively to sales, and that is supported by our regression. Before we continue to the next example, I want to give you a heads up, kind of a warning. Although right here we are kind of making judgment about the hypothesis, looking at coefficients, this is actually not rigorous hypothesis testing because we just make the judgment based on the pure numbers we see, okay? Actually, in practice, if we really want to test this hypothesis, we should take the coefficient and at the same time look at the p-value, okay? Recall in hypothesis testing, we determine whether we have enough evidence in support of the hypothesis by looking at the p-value, or we should use the rejection region approach. So again, just looking at the numbers itself is not sufficient for us to really make a very a very accurate conclusion about whether hypotheses are supported. Okay, so let's take a look at another example and see how we can really use tests on the coefficient. It says a regression model is estimated to explain business unit profitability for a sample of 28 business units for Fortune 500 company. The independent variables are x1, hours, average hours spent in training for workforce, x2, budget, the percentage of the promotional budget used, x3, state, a dummy variable indicating whether the business unit is in Ohio and coded 1 or in Arizona and coded 2. So these are the three variables. And now if you think about the background once such a regression model is estimated, basically a company, okay, or a researcher is interested in finding out the profitability for different business units, okay? So the researcher collects data on the profitability for a Fortune 500 company for the 28 business units, okay? And the researcher also decided the following factors, x1, x2, x3, are important variables that could affect profitability for business unit. Okay, and that's why we're gonna see this regression model includes the three independent variables. All right, now another comment about x3, which again is the dummy variable, it is used to include a categorical variable, right? And apparently, if you look at the data, it seems like this company has business units in Ohio and Arizona, okay? Now, since there are only 2 states involved, we would only create one dummy variable, and we assign 1 to the dummy variable when the business is in Ohio. We assign 0 if it is in Arizona. So what I show you here is the output using SAS. SAS is also a very popular statistical software. It is actually very powerful, widely used in industries, okay? SAS, of course, can estimate multiple regression as well. So this is the output from SAS. The formatting is slightly different from the output using Excel, but both of them will pretty much provide similar information. Okay. And of course, there are a few extras using SAS. There are a few extra outputs using SAS. Let's start with, in this column, the parameter estimates. Okay, this is the column where we can find the values for the alpha and beta. Okay, so these four numbers are the parameter estimates. That means alpha is equal to negative 109.9, and beta 1 is 0.994, beta 2 is 6.6, beta 3 is negative 66.36. There are several things we need to do with multiple regression analysis before we actually use the model to do anything. Now, the first thing basically is similar to simple linear regression analysis. We need to make sure our model is valid. We call that the F-test. I hope you can read it right here. It says F-test, or overall test of the model. Basically, with this test, we're trying to make sure that our model is valid. Okay, so this is another use of hypothesis test, right? You will see in regression analysis, actually, we are also performing hypothesis test quite a lot. For this test, what we are trying to see is, let me type up the hypothesis we're trying to test. Okay, so the hypothesis we're trying to test is basically the null should be the model is invalid, and the alternative is model is valid, which is what we really want to find evidence to support it. Okay, we're still testing hypothesis, and the null is model is invalid. This is just an assumption, and we don't care much about it. Instead, we really want to prove the alternative, which says the model is valid. First, let's take a look at the situation. One, would we find the model to be invalid? Okay, let me show you the original model. Now, if you look at the original model, okay, when we have simple linear regression, we say when beta is equal to 0, x drops from the model, then the model is invalid. Following a similar logic, we're gonna say this time, if beta 1 is equal to beta 2 is equal to beta 3 is equal to all the betas and they are all 0. Think about that situation. If all the betas are equal to 0, what happens to the model? Well, if all betas are equal to 0, then you would see all x's are dropped from the model, and the y is equal to alpha plus answer term. So basically, again, y is not related to any of the x's. This is the situation when we find our model is invalid. That is, all betas are equal to 0. Okay? Some of you might say, hey, I can tell whether all of them are equal to 0 or not, because look at these numbers. They are not 0. Well, let me tell you the difference between these numbers and the betas. These numbers are the estimated value of the beta. They may not be equal to beta. So even though these numbers are not equal to 0, it doesn't imply that all the betas are not equal to 0. It is still something that we need to verify using hypothesis test. Okay, so back to our F-test here, we find that when beta I don't think I can type beta, so I'm gonna write it. If beta 1 is equal to beta 2 equal to all the betas, and that is equal to 0, then we will find the model to be valid. Okay, and we don't want that to happen. Now, the alternative hypothesis is just a little bit special. We don't require all the betas to be different from 0 actually for the alternative. For the model to be valid, we only require that at least one beta is not 0. That's all we need. As long as you find one beta that is different from 0, that means at least one x will remain in the model, and then that means our model is valid. Okay? So in order to test these hypotheses, we will just jump to p-value, okay, because that's all we learned so far. We're going to jump to p-value and recall that we love small p-value, okay? Look at this p-value, it's 0.001, or it's even less than that. So basically, that means we have a small p-value, and the small p-value will enable us to reject the null hypothesis. So let me type it one more time. We love small p-value, a p-value that is small enough, that is smaller than alpha, then the significant level enables us to reject the null hypothesis. Okay? And therefore, for our case here, we are able to reject the null hypothesis due to the small p-value, and therefore we can tell our model is valid. Okay, that's good news. At least we found that one of the axes is related to y, is significantly related to y. At least one x will remain in the model. Okay. Now, naturally, after the f-test, naturally, we would ask, if you tell me among the axes, at least one of them is related to y significantly, I would like to know which one. Okay, if you're telling me at least one beta is different from 0, I would like to know which one or which ones. So the natural next step is the t-test on individual coefficients. In addition, the t-test on individual coefficients will also enable us to test any hypothesis we're interested. Okay? Recall this one. Back here, we were making judgment about the hypothesis based only on these B values, B1, B2, B3. Okay, and I mentioned that that's not rigorous enough. Here's the reason. Actually, we should conduct t-test on each individual coefficient, each one of them, to see whether it's different from 0 or not. Okay, so that is what we call the t-individual test. If we can determine that, for example, this 0.387, okay, if we find that the beta that is kind of estimated to be 0.387 to be different from 0, then we will say, I'm sorry, take it back. If we find out that beta 1, which is estimated to be 0.387 to be positive or 0, we'll be able to tell that hypothesis 1 is not supported. And for this one, for the second, if we find beta 2, which is estimated to be 115.2, if we find that to be positive, we will be able to conclude that hypothesis 2 is supported. So how can we determine that? Let's talk about the t-individual test. T-test, okay? Now the t-test will indicate whether a specific x is significantly related to y. When we say significantly related to y, what we mean is this relationship is confirmed. It is not due to randomness. This relationship is consistent across different situations. Okay? So again, we love p-value, small p-value. If p-value is smaller than 0.05 for the t-test, we will say the variable x is significantly related to y. Okay, we would also say x is useful in explaining and predicting y.